Hi everyone, I'm Jacob Strong. I'll be presenting for Phil here, the tectonic synthesis for the Superior Province. Full transparency, Ross just said, I've got two syntheses going on right now. So there's a bit of a scramble in my brain, and these presentations, although they're important, it's much more important that I get the actual manuscripts complete. And so the tectonic synthesis is about to be finalized in the next week or two, and then I'll send that to Ross before I submit it. And then the isotope synthesis will be taking a bit longer, probably submit it sometime in April. But I'll get on with this one. All right. So this is one of the last questions that Phil posed in his draft of the synthesis, which is, given their unique structural style and tectonic architecture, how are Archean terrains produced? And this is important to understand since significant resources are distributed unevenly amongst seemingly similar geologic terrains. So what I'm going to do in this presentation is I'm going to go through a general understanding of the tectonic evolution of the Earth very quickly, and then I'm going to go through the current understanding of Archean tectonic processes. And then that'll be followed up by the majority of the presentation on focusing on the Superior Province evidence. So secular cooling of the mantle and evidence from metamorphic assemblages suggest shifting geodynamic regimes near the Archean Proterozoic boundary. This is highlighted best by orogenic eclogites, which start to appear in the Proterozoic. There's no orogenic eclogites in the Archean. There's only xenolithic eclogites. And so this suggests that plate tectonics at least began sometime in the Proterozoic. In the Archean, we've got multiple well-preserved Archean cratons, which provide some constraints, but they either yield contrasting interpretations or the overall interpretation is unsatisfying, you might say. Many cratons around the world are interpreted as forming by or assembling by plate tectonic processes, whereas there's a few rarer cratons which are hypothesized to have formed by non-plate tectonic processes. So I'll start with the Pilbara craton, which is probably one of the best studied in the world. It's also one of the smallest. In the Eo to Paleoarchean, the Pilbara evolution is dominated by plume-driven vertical tectonic processes, and this is highlighted by the structural motifs of the granite domes rising between metavolcanic and metasedimentary keels. After the Eo to Paleoarchean, the Mesoarchean history of the Pilbara reveals a limited but spatially variable horizontal tectonic processes, which are attributed to a dripduction or sagduction event in the Mesoarchean. The sagduction event is used to I forget the word. It's used to demonstrate that you can produce high pressure, medium pressure, low pressure TTGs without a subduction environment. So in contrast, most other Archean cratons involve some sort of terrain accretion, consequently some type of subduction-like process. And this is needed to either explain the assembly of distinct terrains and or to explain other factors such as arc-like geochemistry of volcanic sequences. And this has recently been identified in the Yilgarn, where you have these volcanic sequences in the Yuan-Anmi terrain, which are central in the Yilgarn, and they're attributed to subduction of the narrower terrain below the central Yilgarn and production of these sort of subduction fluid metasomatized volcanic rocks, which are restricted locally to the CIZ. I forget what that is exactly. In North America, the formation and assembly of Archean cratons generally have histories that are analogous to the Yilgarn. The Neo-Archean evolution of the Slave Province generally invokes accretion of several terrains in the Neo-Archean, but intraplate rift-like settings have also been deemed plausible. In the Superior Province, is no different. It's either been interpreted as a collage of accreted terrains or as a single coherent craton that grew through autochthonous processes. So there's general consensus that when and how plate tectonics began is poorly understood, with the possibility that we may be reaching a limit of understanding due to the difficulty of testing increasingly complex models. Mark Harrison in 2024 discussed this in detail. And so what, if any, inferences or evidence does the Superior Province offer? The Superior Province is unique because it's uniquely situated to tell us something because it's the largest Archean craton with crustal components ranging in age from 4.0 to 2.6 billion years. Part of the problem with the Superior Province is that it's dominated by volumetrically lesser Mesoarchean crust relative to a significant amount of Neo-Archean magmatism. And it's the mosaic of Mesoarchean and Neo-Archean crust that was built upon older crustal fragments, which has resulted in two classes of tectonic evolution models for the Superior Province. So I'll start with the allochthonous terrain model, which is the subduction accretion model. And it's based on the formation and evolution of terrains through plate tectonic processes. In this model, the terrains are bounded by sutures, which are either faults or discrete deformation zones that juxtapose terrains with apparently distinct histories. Calc-alkaline magmatism is attributed to magmatic arc settings, and the onset of Neo-Archean metamorphism gradually becomes younger in terrains towards the south, which appear to support this model. Some of the issues and also supporting evidence is that one, the majority of volcanic rocks in the Superior Province actually show crustal assimilation trends rather than fluid flux melting. However, there are some rare arc-like volcanic sequences, the Schreiber-Hemlo and the Birch-Uchi, which provide some of the most convincing evidence for subduction or subduction-like processes occurring in the Neo-Archean Superior Province. And so these two sequences make it pretty unclear. It's unclear whether subduction-like processes occurred at terrain boundaries or marginal to the craton. Some of the other inconsistencies with this model is that it requires the assembly of multiple arcs, and therefore you have to subduct quite a lot of oceanic material to produce those arcs. And so you can imagine that these terrains are pretty far apart, and if they're so far apart, well, where are all the other Archean cratons when this is going on? I think there's another inconsistency, but we'll just move on. Geophysical results from lithoprobe were originally interpreted in a plate tectonic framework, but new and old data have been interpreted by various others as potentially unrelated to Archean plate tectonic processes. So the non-unique interpretations that arise from some of these inconsistencies led to an alternative model based on mantle flow, autochthonous growth, and subcretion rather than subduction, as well as other non-uniform formatarian tectonic processes. So in this model, the older Edo to Paleoarchean terrains represent fragments of a disaggregated protocraton, while the younger Meso to Neo-Archean terrains represent regions of juvenile growth, mostly in Archean rift-type settings. So in this model, Bedard argues that mantle upwelling and outflow from below the Hudson Bay terrain at around 2.78 to 2.74 billion years resulted in disaggregation of the protocraton through formation of juvenile Archean rifts, which also detached the older fragments. The southward trend for the onset of metamorphism in terrains, originally identified by Percival between 2.72 and 2.68, can potentially be explained by ending or reversing the mantle flow and sort of accreting these terrains by subcretion rather than subduction. This model argues that mantle currents generated by periods of mantle overturn are able to explain various aspects of the Superior Province geologic evolution. This model is also argued to account for other aspects of Earth's geologic evolution, such as the formation of a significant amount of I forget the rock type. We'll move on. So, as you can see, solid evidence is pretty elusive, but geochronology can provide some insights in a similar way that stratigraphic assemblages of the American versus African continents were used to support continental drift about 100 years ago. Since the largest Archean craton contains within itself 3 Eoto-Paleoarchean fragments, we can attempt to determine if these older terrains have similar or different Eoto-Paleoarchean evolutions. And so what we can see is it's a little bit chaotic, but you'll find that there is distinct overlap. You'll find at 3.8 to 3.7, 3.65 to 3.6, and then there's a variety of other overlapping Paleoarchean ages, 3.5, 3.45, 3.4, 3.3, and 3.17. But most important is not really these older, the correlation of these older ages. One of the most significant correlations is actually this 3050 metamorphic event, which you find in the Minnesota River Valley terrain, Winnipeg River terrain, North Caribou terrain, and Hudson Bay terrain. And so this is a pan-superior event, metamorphic event that occurred at 3050. And right after 3050, we start to find the North Caribou terrain forming by plume and platformal sequences developing as well. So here's another figure showing the isotope data. I'm not going to go into this in too much detail. The vertical bars highlight the Eoto-Paleoarchean overlap in magmatic ages. There's limited overlap in the hafnium isotope composition, but you can see there's a general trend. There's an older crust which is being assimilated or influencing this younger magmatism. One of the most significant parts of overlap that we have is between the Winnipeg River and Hudson Bay terrain, which overlap with juvenile crust at 3.3 billion years. And this crust, as you can see, it starts to trend down these evolution lines. So based on this, I am fairly convinced that these terrains record a similar magmatic history, although their isotopic composition is somewhat variable. I think the distinct overlap in discrete ages that we find here are pretty diagnostic that these are correlated terrains from an original protocraton. So if the oldest terrains are related, that implies that the intervening granite greenstone terrains formed through some type of autochthonous growth. And this is consistent with 3.05 to 2.9 juvenile crustal growth associated with plume-related magmatism in the North Caribou terrain. And additional evidence, like I've already described, for autochthonous growth, and that all these terrains were already interconnected in some way, is this 3.07 to 3.03 billion-year-old zircon growth event, which occurred in the Hudson Bay, North Caribou, Winnipeg River, and Minnesota River Valley terrains. So another potential process that may be involved in Archean tectonics is lithospheric delamination. Delamination has some potential to explain greenstone belt formation convergence and possibly rare arc-like volcanism. But similar to most other Archean tectonic processes, there's a significant amount of speculation required. And it's also pretty unclear how you would test for this because the majority of action is occurring below the bottom half of the crust. So there's essentially nothing occurring on the surface. So this is a very hard process to test for. And so in summary, there's really no clear explanation for when plate tectonic processes started or exactly when tectonic processes operated during the Archean. In the Superior Province, the location and orientation of inferred subduction zones is difficult to assess because there are no hallmarks of relic subduction zones or accretionary belts. That's probably something I missed, which the so-called sutures don't really have mafic mélanger. They don't appear to be any similar to Phanerozoic or Proterozoic sutures, accretionary sutures. We have determined that the older Eodo-Paleoarchean gneiss terrains have a similar history and also experienced a Mesoarchean zircon growth event between 3.07 and 3.03 billion years. These temporal similarities, there is also temporal similarities in the Meso to Neo-Archean granite greenstone belts, which support an autochthonous crustal growth and tectonic evolution model. And that's that.